spider. It's quite
well, that's how I feel about it. I mean, I'm dying to get this shot in my arm. As you know, I have 2 kids that live abroad, right? So
I'll let you know that we are online on YouTube.
Okay, I'll stop chatting.
I think we can wait for 1 more minute. Is that okay with you?
I'm yours for next hour.
Okay, just 1 minute, and then I will do this short introduction. We will start. Okay, well, let's start. Hello, everyone, and welcome to another talk in our webinar series. This webinar is also being streamed live on YouTube. You can find the link on our website, or you can access it on our YouTube channel, LIneA MCTI. Today, we have Željko Ivezić from the University of Washington talking about the Legacy Survey of Space and Time, the greatest movie of all time. Željko, thank you very much for being with us today, and the floor is yours.
Thank you, Rodrigo. Thank you for inviting me. I'm now trying to share my presentation. So can you confirm that you can see it?
Wow, still loading. Yeah, now it's up.
Excellent.
But it's in the other view that you had, okay? You show the...
Is it full screen now?
No, not full screen.
Not full screen?
No,
okay.
Not yet. You have the other setup where you...
Yes, the supporting
slide.
Slides.
Oh, I see. Because I see only one screen, and I did exactly the same thing we did when we tried it a few minutes ago. Let me now repeat the exercise. Now seems stuck. So what do you see now?
Nothing.
Nothing. Okay, so let's start from scratch. Share screen. We are screen sharing. So what do you see now?
Yeah, now we see it. You just have to put in presentation mode.
Okay.
Now is the correct view.
I'm going to presentation mode. So on my side, it looks
now you went back to the other mode.
Okay, I don't understand what's going with. One more, and if that doesn't work, I'll switch to PDF instead of PowerPoint. I have 2 little movies, that's why I'm using PowerPoint, but if it keeps doing this. Once more.
Now you're still in the other mode with this slide now. Next slide.
Yeah, wasting valuable time. But sorry about that. It looked like everything was fine first time.
It's fine. No worries. But you had it at some point. I mean, I actually saw. You just had to put in.
When we tried it first time.
Okay, here we go. Now we just have to show the slides.
So now it looks good for you?
Now it looks good. Just have to show the slide. I mean.
So did it go to second slide?
Yeah, he went to the second slide. The other problem is that we see on the left all the slides. That's a.
Okay, that's
just
exactly now.
yeah. So you just
So
have
let's
to
hope
present.
for the best. I went to slideshow mode again.
Okay, wait a second. It's reloading. No, it doesn't work. When you go to this mode, it goes back to the outline. Just show the way you were. Just let's go move on.
Okay, we are.
You see what I mean? I mean, the first time you show, it shows your slides, not full screen, but with the others, supporting slides next to it. And then when you try to make presentation mode, it goes back to the one that you showed the next slide.
It's something with PowerPoint setup, who knows? So we will give up on those two little movies and we are going to do PDF.
Okay, now that's fine now. Okay.
All right, I hope now it looks fine.
Yeah, it does.
You have full screen and everything is fine?
Yep.
Finally, okay, so we can start. Thus, copies, these slides can be accessed at this web link. If anyone finds something interesting or wants to record a reference, there will be some references in my talk. You can get this entire slide deck from this link, ls.st LIneA 2020. So thank you again for inviting me. I'm going to basically address three themes. I will introduce LSST and the reason why we are building a new observatory to deliver LSST. Then I'll give you a quick tour through the construction. We are still not done yet, but we are almost there. So I'll show you some pretty pictures of the construction of the summit and the main elements of the system. And then at the end, I'll go quickly through some illustration, basically very brief illustration of big data challenges that will be posed by this huge data set. So I can't see the chat. So if you have a question that you want to ask, then just interrupt me if it's something that prevents you from following the rest of the talk. If you have, on the other hand, something that can wait for the end of the talk, then just type it in the chat so you don't forget it. And then I will answer all questions at the end of the talk. So as you know, there are different ways of doing cutting edge observational astronomy. And so if you want to excel, you could build a large telescope on the ground. And the biggest ones being built now are 30, 40 meter range, the European 40 meter, 2 US 30 meter telescopes led by US, the other countries involved. The other way to do cutting edge astronomy is to put your telescope on a spacecraft and avoid atmosphere and go above the atmosphere. So you have much better sensitivity because there is lower background and then you have much higher angular resolution. And then over the last few decades, it was demonstrated by many surveys that survey mode, thanks to the development of sensor technology and of information technology, you can get huge data sets, you can process them, and you can observe this way, you can measure many objects at the same time. And then because of the huge sample size, you can do things that you cannot do with the first two approaches, where typically you observe only a small number of objects. And by small, I mean it's not billions. It could be millions, but it's not billions. So SDSS was one of first digital color surveys that very forcefully demonstrated that you can do cutting edge astronomy with survey approach to your observations. And so starting with SDSS 2 decades ago, today, surveys like, for example, PanSTARRS are already detecting billions of objects. Gaia has 1.4 billion objects in its catalogs. So that huge number of objects gives you huge statistical power for studying history and the history of structure of growth of structure of the universe. So there are many things you can do with these billion object data sets that simply you cannot do with smaller data sets. That's why we want to have them. So this development, rapid development of surveys led to a new paradigm in astronomy where we don't follow anymore the classical scientific approach where we say, I have hypothesis So now what data do I have to collect to disprove this hypothesis or test it? With data-driven huge surveys, you ask what theories can I test given the data I already have? Or I paraphrased JFK, President Kennedy, by asking, ask not what data you need to do your science, ask what science you can do with your data. That's basically the survey approach to astronomy. So you, with all these great surveys that already exist, like Pan-STARRS and Dark Energy Survey and Gaia and many others, you can ask, why would you want to spend another billion, actually more than $1 billion on another sky survey? And there are multiple other missions, and I have just some of these most impressive ones. So we have this giant ground-based telescopes. There are two great new Hubble successor telescopes, James Webb, which will be Hubble with a much bigger mirror, and Nancy Grace Roman, until recently called WFIRST, which will have 100 times larger field of view than Hubble. So these two are like super Hubble. And LSST, actually, Rubin Observatory, is the cheapest, the least expensive project on this list. And yet it will be very competitive. So just brief mention of terminology. When I say LSST, I mean the actual data set, the actual astronomical survey. The observatory that will deliver this data set was earlier this year named after Vera Rubin. It's called Vera C. Rubin Observatory. As you probably know, Vera Rubin was instrumental in demonstrating that there is dark matter out there that we can see through gravitational effects, but it does not emit photons. So to honor Vera Rubin Observatory will be called Rubin Observatory. And the first 10 years of that observatory will be used to deliver LSST, a legacy survey of space and time. Until this year, it was altogether called LSST, and it stood for different words. Now it's a legacy survey of space and time. So LSST, obviously, according to this slide, will not have the largest mirror. Actually, it will have relatively tiny mirror of 8 meters, but it will have by far the largest product of the mirror area and the field of view size. ELT, TMT, GMT, all these telescopes have very tiny field of view compared to LSST. And that allows you then to scan the sky rapidly. And so this slide that I stole from Andy Connolly's TED Talk demonstrates how can you scan the whole sky with LSST. So the big blue circle with 3.5 degree diameter or 7 full moon, that's the field of view of LSST. And that's much larger than typical large mirror telescope. They typically can't even see the full moon, let alone 7 across. And so these red circles on the sky illustrate how we will scan the sky. And each of these exposures, we call them visits, will last about 30 seconds. And that in that circle, there will be about 10 million galaxies. This is about 10 square degrees. We aim to cover 20,000 square degrees approximately. So there are about 2,000 circles on the sky that will cover LSST area. So you will have 20 billion galaxies. It will be the largest galaxy catalog ever. It will be first time that astronomers will have cataloged more objects than there are living people on Earth. We still don't have as many astronomical objects as living people on Earth, but that will happen with LSST. And to illustrate how things change when you go deeper and more sensitive, I'm comparing here SDSS image. This is 3.5 arc minutes on a side. So it's roughly 1/10 of the moon's diameter, full moon's diameter. So it's very tiny area on the sky. There are a few hundreds of galaxies in SDSS image. And then I will show you image obtained by the Subaru telescope that goes to the same depth as LSST. And now you can compare. This is exactly the same part of the sky, but if you go from the 22nd magnitude limit of SDSS to 5 magnitudes deeper or 100 times in flux, the deeper you go on the sky, the more objects you see. And so this explains why SDSS had under billion objects, but with LSST, we will have 40 billion objects. So roughly 2 orders of magnitude, factor of 100 more objects in LSST than in SDSS. I just love flipping between these two. It's very impressive. Actually, this one I have on my wall in my kitchen. Robert Lapton made foot by foot, roughly speaking, printouts, and it looks pretty on the wall. So let me go back now to science drivers for LSST. We have 4 science themes that we use to both justify the project to the funding agencies and to use these science themes to quantitatively size the system, to decide, for example, how large mirror we have, how large field of view we need, how many pixels we need, etc. So these 4 are studying the history of the universe, basically cosmology, using various probes. And I'll show you in a few slides what do I mean by was Einstein right. Then we will get these observations by chopping the total exposure time for each point on the sky in about 1,000 pieces, 1,000 30-second visits that will be spread amongst the 6 filters, similar to SDSS. So in each filter, there will be of the order 100 observations. So we will also open the faint time domain. And because we are opening time domain and seeing everything that changes in brightness, we also see things that change in position. So we will have great sample of asteroids, about 6 million asteroids in the sample, which is roughly a factor of 10 increase, and with much better data, with light curves, with precise colors. And then, of course, we'll also have of the order 10 billion stars in the sample that we will be using to study the Milky Way structure. And most important aspect of this data set is that it serves all these science programs. So there will be no chopping of the observing time into 4 pieces and give 1/4 or whatever would be the fraction to each of these 4. Basically, we designed a survey that will be capable of delivering all this science with a single data set. The same images that we will be using for cosmology will be used, for example, to study asteroids and to get their orbits. It will be the same data set. So this data set follows quite simple observing strategy. So about 90% of time, we will be spending on the main survey. And that main survey is seen in green in that lower left corner. This is 8 of projection of equatorial coordinates. And the color is the number of visits, how many times we will observe certain point on the sky. And this particular image is for G, R, and I filters together. So it goes up to about 500 for this combination. The total number of visits for the main survey is 825 is the requirement over all 6 bands. And then the remaining 10% of time will be used to increase the parameter space by, for example, covering North Ecliptic Spur, where we will get trans-Neptunian objects by factor of 2 increase in the sample size, South Celestial Pole for legacy reasons and stability of calibration, etc. But the main survey is this green area that has area of about 18,000 square degrees. That's the requirement. And it will include about 40 billion objects. And all the images that we will collect is roughly 100 petabytes of data, 100,000 terabytes of data when you add up all these images. Because we will have multiple copies of data products, there will be metadata, etc. We are sizing our system at year 10 for about 500 petabytes of data. But the raw image size without anything else will be just about 60 petabytes of data. So the survey will last 10 years, and we hope to begin in the fall of 2023. So let me now quickly go through the main. I cannot go through all the science themes, but I will just touch upon cosmology and a few other things. As you know, over the last decade or so, many measurements pointed out that the universe is accelerating. The expansion of the universe is accelerating, and if you want to simultaneously explain that acceleration and the growth of structure, which is illustrated by this dark matter simulation in the top right corner, if you want to explain all these observations, you can do it, which is quite impressive because they come in various flavors, these observations. But the price to pay is that you have to postulate 2 components of the universe that we don't really fully understand. One is dark matter, and then the other one is dark energy. So the good news is that we have a variety of very diverse measurements of the universe, and we can build a relatively simple model which explains them all, but we are unhappy because we don't know what dark energy is. At least for dark matter, there are some possibilities from the particle physics world, but for dark energy, we are clueless. But indeed, as I will argue later here, I don't have details, so let me just briefly say it here. When we observe the universe and when we start interpreting these observations, we postulate that the general theory of relativity is correct. And then we get the result that we must put dark energy into our equations. But if you postulate that you have different theory of gravity, you can also explain observations without dark energy. And that's the origin of this question: was Einstein right? Basically, with existing data sets, we cannot tell apart these two possibilities. But we believe that with LSST dataset, we will be able to distinguish, using various methods, possibility that GR is wrong from the possibility that we have dark energy as new major constituent of the universe. So the different methods that we can use in astronomy to measure cosmological parameters, the modern ones include 4 that can be done with LSST. Obviously, we cannot do CMB measurements because that's totally different wavelength band. But we can do weak lensing, galaxy clustering, and Baryon Acoustic Oscillations with our galaxy sample. Again, we will have of the order 10 billion galaxies, and we estimate that there will be about 4 billion galaxies in our so-called gold galaxy sample, defined by I magnitude less than 25, that will be used for cosmology because it will have relatively precise photometric redshifts. And then, because we are opening the time domain, we will have few million supernovae that are standard candles and are also used to measure expansion of the universe. And we will have the supernovae sample will extend all the way out to the redshift of 1 or so. So that's the reason for cosmological reasons for doing LSST. And when we take this data set, we believe that we will have, with photo Z's, fractional errors in distance of the order 1%. And by using multiple probes, we will be able to answer the question whether the recent acceleration is due to dark energy, assuming GR is correct, or perhaps we need some modified gravity theory. We need to modify GR and explain observations without the need for dark energy. That's one of the key driving questions behind LSST. But in addition to cosmology, when you have billions of galaxies, you can also do fantastic galaxy astronomy, galaxy formation and evolution. And here is again one example of how much better LSST dataset will be. On the left, we have again 3x3 arc-minute image, color composite of some boring galaxy from SDSS. I call it boring because there aren't many details in this galaxy. It's basically elliptical distribution of light. But if you go deeper, especially if you have much deeper surface brightness limit, and on the right, you have exactly the same part of the sky on the same scale from music survey from Eric Geweiser et al. Paper. And now you can see if you go much deeper, roughly 5 magnitudes, then you can uncover detail that is simply not visible in SDSS image. You can see this tidal tail around that galaxy that now encodes details about gravitational potential about that galaxy, including the dark matter distribution. And today we know of perhaps few dozen, maybe 100 such examples of galaxies with well-formed tidal tails. But with LSST, we predict it will be millions such objects in the data set. So it will be completely new statistical field to study. How do you quantify these tidal streams, etc. And then also with billions of stars, you can do fantastic science. And often people say, well, you have no fighting chance with Gaia. Gaia is so precise that you can't do anything from the ground that would be competitive with Gaia measurements, which is more or less true if you limit yourself to magnitudes greater than 20. But because LSST will go with each observation 5 magnitudes deeper, roughly 4 to 5, and with coordinate data almost 7 magnitudes deeper. There is also regime in which LSST will be the best game in town, even in the context of proper motions and trigonometric parallaxes. So here is just one figure from this review paper we published 2 years ago that demonstrates that it's almost like intelligent design, that you designed the two surveys to work together. You have one in space at the bright end, and then what you can't do in space, you do from the ground with LSST. So there will be a lot of fantastic science once we have trigonometric parallax and proper motion measurements from LSST. And here is summary, roughly what will be extent of our data set with main sequence turn-off stars. So these are the most luminous main sequence stars that you can see. And the reason why you want main sequence is that they are most numerous stars, much more numerous than, for example, red giants or horizontal branch stars. So you can study the structure, you can study their distribution and kinematics with much higher fidelity level and with much better volume resolution. So using this tracer, I'm showing in the middle this little insert that's real map based on SDSS. And these are counts of stars. You can clearly see the shape of the disk in it, and then it extends to halo. And that was out to about 10 kiloparsecs. And then with dark energy survey, that most of you are very familiar with, you can push this now to 40 kiloparsecs, but only over about 12% of the sky. And then with deeper data from LSST, we will push this out all the way to the putative outer edge of the Milky Way halo at 100 kiloparsecs, and you'll be able to do it over half the sky. So it will be a major step forward. And if you wonder if there are any stars there to study, the background is a simulation from James Bullock that shows that according to our n-body models, you will see stars all the way out to 100 kiloparsecs or so. And halo stars are especially interesting because they have long dynamical times, and they still encode the history of the galaxy evolution. They are not mixed so much as the disk stars are. So let me now go back to the system itself. Let me show you a few photographs, basically, of the components of the system. So as you know, LSST will be in Chile at Cerro Pachon, which is next to Gemini South. It's next to CTIO Observatory, to the Blanco telescope. There will be 2 fiber links. One will go through Brazil. As you know, this is a basis for agreement between Rubin Observatory and Brazil for collaboration. Then once they arrive to US, this is old map that still has NCSA, National Center for Supercomputing Applications in Illinois. Recently, we changed the location for our data center. It will be instead at SLAC, which is next to Stanford University. Used to be called the Stanford Linear Accelerator Center. Now the name is SLAC. That's the place that led the construction of LSST camera. It's a Department of Energy lab, and because DOE will fund 50% of operation costs, we had to move the data center to SLAC. And then the other major data center will be in France that will do 50% of processing, and we will also have the 3rd copy of the data in France. So that's how the site looked before 5 years ago when we started construction. This is one funny image when I tried to do some useful work, but the door was closed, so I didn't do much. And the reason for it is that you can see in the background Gemini South telescope, and then all the way to the left is SOAR telescope. So we have that's very close. You can walk from one to the other. Then 2 years later, you can now see the outline of the observatory. Top left shows the cutout of everything that we will have inside the observatory. You can see the coating chamber for coating the mirrors. You can see elevator in the middle that takes that mirror from the dome to the coating chamber, etc. This is how it looked about a year and a half ago. So we were hoping, at that time, we were still hoping that we would start operations in 2022. However, because of COVID, we lost about a year. So now we expect first flight will happen in about a year and a half from now. And operations will start in the fall of 2023. So fortunately, so I will skip, that was little movie that, since this is now not PowerPoint, I cannot show. This is most recent image, 2 days old, from the summit. You can compare to the previous one. You see the dome is just the construction of the dome. There is no cladding on it. And about a month ago, we got Italian crew from the company that designed and constructed the dome to come back. And so the dome is almost enclosed. And we are hopeful that the Spanish company will be able to send workers in January to resume the work on the assembling of the telescope mount assembly. We're still waiting for their visas, but we are hopeful. If that happens, then the telescope would be assembled by the end of 2021, and hopefully during the calendar year 22, we would have first light and get first images from the system. This is the telescope. It was fully assembled and tested in Spain in a company called Astrofieto. They measured everything, demonstrated that it met its requirements. Then they disassemble it. All these pieces, all this entire construction is already at the summit, but most of it, it's not assembled yet. And that's our main goal for 2021, to basically be able to make such a photograph inside the dome by the end of calendar year 21. So why is LSST so special, or more precisely, why is Rubin Observatory able to deliver LSST? As I said at the beginning, the trick is that Rubin Observatory system has the largest product of the mirror size and the field of view size. And here I compare Gemini South mirror, which is 8 meter, actually even slightly larger effective area than our mirror. You can see this giant hole in the center. I'll show you in a minute what it is. So it's even better mirror from that point of view. But when you look at the field of view, this is tiny field of view in the upper right for Gemini South, and you can now see how much larger field of view LSST has, or Rubin Observatory. So that's the key point. The reason that we can get LSST from the Rubin Observatory is this huge field of view. If you wanted to get a survey like LSST using Gemini South telescope, it would take you 1,000 years, not 10 years, as it will take with Rubin Observatory. That's the key point. And the reason why we have hole in the center, it's not actually a hole, it's one solid piece of glass that has two different surfaces. The outer one is primary mirror, and then the photons are reflected towards the secondary mirror, which is in the center. Then photons go to the inner portion of this primary tertiary mirror. So the inner portion is called tertiary mirror. Then it goes through 3 optical elements, 3 refractive elements, and then the camera sits inside this hole in the secondary mirror. So with this construction that uses 3 reflecting surfaces, it is possible to achieve very large field of view without optical distortions that you would have with 2 mirrors, and that would prevent you from doing very precise galaxy weak lensing measurement. So we maintain large field of view with exquisite image quality because we have this rather unique optical design. And the mirror was produced in Arizona. It was spin cast, so it's a furnace that rotates, and then glass is heated until it's liquid, and the rotation causes the top surface to be parabola as you want it to be for mirror. And then you cool off over a few months, you decrease the temperature until glass solidifies again. And so you already have the primary mirror more or less to the specs, and then the inner part, the tertiary mirror, needs to be polished, which then sped up the process of producing this mirror. And this photograph was taken when this first step was done. So this red stuff around the mirror is basically the edges of the furnace. This whole construction can rotate with about 1 rotation per minute. And then after polishing the inner part, now you can see the mirror still in Arizona in the lab before it was shipped to the summit. Now it's at the summit, as well as all the other optical elements, everything is at the summit. The camera is also a great piece of engineering. It is the largest astronomical camera ever produced. It is 3,200 megapixels, and it's giant. You can see a person next to it. It's like small SUV. The reason we can get 3,000 megapixels into the camera is modular design. So each of these red squares in the left is what we call a raft. You can see them on the right-hand side, pulled out of the focal plane. They have 9 CCDs, 9 4K by 4K CCDs, and each one has its own electronics underneath. And so each of these rafts is essentially an autonomous camera, and you can replace one with the other one. And so we have 21 of these rafts. We have 189 CCDs in the camera. That's how you get to this huge pixel design. There are some other tricks. You want to have very short readout time. Ours is 2 seconds. So each of CCDs actually has 16 segments that are read out in parallel to enable 2-second readout and so on. I can't go into too many details. So this camera is huge. For example, if you want to display image from the camera, that's not trivial. If you wanted to have all these pixels, you need 1,500 high-definition televisions. So this little photo montage shows how it would look like if you wanted to display every single pixel from LSST camera. You'd have to put 1,500 TVs on some building in order to see the image. This is one of the lenses for the camera. It's the largest lens ever produced. You probably remember your early lectures in astronomy where you probably learned that the largest telescope refractor ever produced was the Mpix refractor, 1 meter. But this is now larger than that lens. This is the largest lens ever produced. It's not Mpix anymore. And this was also a little movie of how we will change filters, which now I cannot play, but basically these filters rotate around the axis of symmetry, and then there is a robotic hand on the right that can take filter, take it out, rotate the other 4 around, put it in, and replace a filter. Unfortunately, we can only put in the camera 5 filters out of 6 that we have. So the plan is to replace one of those 5 with the one that is missing, perhaps once or twice a month. We'll see that in operations, what is the most efficient way to do it. So for example, during bright time, you don't use U-band, you don't need it, but if you go to dark time, you might want to use U-band too. And few pretty photographs from SLAC clean room. This is where this camera was built. This is its birthplace. You can see our team at SLAC assembling it. And just this year, we had a press release showing image from the full camera. So the camera is assembled, it exists, and it's taking images. This is one of these rafts. This is now, so here the picture shows still sync, but by the beginning of this year, it was all completed. And few quick words at the end about software. So our goal as the project is not just to produce these images and give it to people to use, but actually to process these images and to produce data products that are essentially science ready. So you want to have catalogs, you want to have lists of objects with their positions, with their flux measurements, with their shape measurements. You want to connect them through time axis to get light curves, so that there is a lot of processing to be done to enable science with this data set. So we have a lot of software to produce. And here is, for example, just our science pipelines. There is much more software we need to produce, but the key astronomical aspects are encoded in our science pipelines. And so here we have 8 major pipelines that we are producing. The standard processing, like for example, what SDSS had, is number 1. You get raw data and you produce pretty calibrated images, where essentially each pixel then gives you flux instead of electron count. And instead of pixel coordinates, you have coordinates on the sky. That's the first one. But then we also need to produce software that will be co-editing these images so that we go deeper and that we get to these 20 billion galaxy count, and also do measurements on these objects that will be free of systematics that may prevent us to accomplish our science goals. That's especially important, for example, in the context of weak lensing for galaxies, where you have to measure shapes with very small systematics, or also with photometry, which will be used to get photometric redshift estimates with very small systematics. And then on the right-hand side, these 5 to 8 pipelines, what they will do is to take each new image and subtract it from coded image that was produced in pipeline 2. And then in that difference image, we will look for all the objects that either change their brightness or change their position. And then we will separate those that move from those that are static but change brightness. We will measure their properties, and we will issue alerts about new objects we detected within 60 seconds of closing the shutter in Chile. So we have specifications that you should be able to get information about all the new objects we have in our images within 60 seconds. And this is illustrated here. So there are 2 examples. In the first row, you subtract image 1 from image 2, and you get difference, and there is nothing in it because nothing changed. But in the bottom row, you have 2 images, and there was new, probably asteroid or maybe some cosmic explosion in image 2. And when you subtract one from the other, you see a new object in difference image. And so now software goes and finds new object in difference image, measures its position, its brightness, its properties, and we pack this into about 100 kilobyte alert. And we have few thousand per each visit of LSST, up to 10 million during night. And we issue that for people to then filter, decide what is most interesting science for them, and then deploy other assets they may have to do follow-up observations, either to provide better temporal resolution or to obtain spectra, for example, etc. So we expect up to perhaps 10 million per night, so which will give you together, when you average over all other parameters, about 10 billion alerts during 10 years of LSST. And so here is another example. I just wanted to point out that it is not just point sources that you find in difference images, but sometimes you have very complex structures. And I love this example where in Macho survey, they discovered this effect that there was supernova in the center of that circle on the right. So science image is on the left. That's the one that you subtract from the other one that is time averaged one. And to the eye, it looks just like this one. You can't see much. But now when you compare the two, you can then detect this expansion of the shell around supernova. And it's just a beautiful example of what you can do with modern technology. And so let me now conclude with a couple of slides about how hard it will be to handle these huge data sets to do your science. So we did go in astronomy in the last 2 decades or so. We went from megabytes to today terabytes of data, and with 10 stars, we already entered petabyte domain, and with LSST, we'll have of the other 100 petabytes of raw images. And so this is now becoming hard to handle, and we need to engage people from other fields, like, for example, statisticians, computer scientists, mathematicians, to help us analyze this data. So this is my list of things why it is hard when I talk to statisticians, when they ask me, so why is astronomy hard? Why do you want to talk to me? I said, well, one reason why it's hard is that we have huge data volume. It's petabytes. So you can't just handle this on your laptop. You have to do something more serious than your laptop. Then we also have huge numbers of objects. We have billions. If you want to do statistics on them, you can't, for example, just take Microsoft Excel spreadsheets and do it in spreadsheet. You have to write at least some special purpose code. Then we have highly multidimensional spaces. And these now, people are beginning to handle this in other contexts, which is good, but it's still not trivial undertaking. We often have unknown statistical distributions. We are working in the discovery mode often in astronomy. And so when you want to optimize your statistics, you don't know optimize for what. Then with time series data, there are literally tens of thousands of books written on time series analysis because it's important in engineering. but 99.9% of these books, I didn't count it, this is just a figure of speech. The majority of these books are designed for regular sampling as it happens in industry. And in astronomy, we have very irregular sampling, and most methods that are regularly used in engineering do not work with our data. To make it worse, we also have non-negligible errors, and they're heteroscedastic. That means they vary from measurement to measurement. They are not homoscedastic, which is the case when you have errors, but you know them, and they're always the same for all measurements. We know in astronomy, the fainter is the source, the larger is the error, and many methods cannot handle that, and so on and so on. So it will be hard to sit down and immediately produce science with such data sets. We need to prepare ourselves in advance to be able to handle it. And so the bottleneck will not be just that you have data or you don't have data, but you need to have methodology to extract useful and reliable information and then compare to models to understand, to learn something from this data set. Another way to look at it is that we have about 40 billion objects measured. And for each object, we have about 1,000 epochs. And if you just assume it's just 10 numbers per each image, it's many more. But for the sake of argument, let's just say we have 10 numbers that we measure in each image, and we have 1,000 images per object. So that's 10,000 numbers for each object. So it is 10,000 dimensional space. And now it's populated with about 40 billion points. So that's basically what we need to do, which is much harder problem than what we typically do or people in other fields. What we want to do is similar what people do. It's characterization of known objects. So in the bottom left, you can see three-dimensional version of some data distribution. And there are different shapes. There are different clusters in that shape. And we already have methodology to easily find these clusters. Then we want to classify these clusters. We want to learn what they're made of, maybe get follow-up spectroscopy in case of LSST. That can be done too, quite easily in low dimensional spaces. And then you want to look for things that are different than anything else, like these question marks and handful of sources that do not belong to any of these four major clusters. We can do all of that today, but we can do it only in much lower dimensionality spaces with many fewer objects. Nobody yet can do 10,000 dimensional space with 40 billion points. So we will have to devise methods for how to do that. And so in the context of alerts, when you have new alert and you want to ask, is that something unusual that I should deploy my 30-meter telescope for? Or is it just an error in measurement? Or is it just some boring astrophysical source that we have thousands of? And so this is similar to looking at this image, and you need to teach your computer to find what is unusual in this image. Where is the out? And if you sheep that has blue sweater, that could be one of them, but that's so obvious that you would rather call it's a population of different sheep. The real outlier, I would say, is here. This is what you need to teach your computer to find. Something that is subtle, but yet it's telling you you're looking at something different. You see this sheep, all the other sheep are sleeping, but this one is looking at you and asking, when is first light from LSST? So I will stop here. First light from LSST hopefully will be in 2022, and the regular survey operations will start in 2023. So main points in my talk are that we live now in an era when astronomers will be producing catalogs with tens of billions of objects. So we reach the point where we will have more astronomical objects than living people on Earth. That never happened before. I also want to point out that it's not just astronomers that build observatories like Rubin Observatory. It is also physicists, mechanical engineers, electronics engineers. We are now in a regime where astronomers cannot do it alone anymore. All the easy things are already done. And the harder things that we want to do will require interdisciplinary approach. And that approach we need not just for building the observatories, but also for interpreting, for understanding our data. And that includes a lot of modern data mining machine learning tools. So we need to talk to statisticians and we need to talk to computer scientists. So astronomy is becoming increasingly multidisciplinary endeavor. So for younger colleagues who may not know much about LSST, but would like to learn more, there are these 3 links in the top left. LOP is LSST overview paper, which is a great entry point to the whole idea of LSST. If you want to learn what kind of measurements LSST will be doing with its science pipelines, the second link is DPDD, Data Products Definitions document. And the last one is Science Requirements document. And then in these 3 references, then you can find many other references, including the science book for LSST. So I will stop here, I will stop sharing, and I will happily take your questions.
Thank you very much, Željko, for this very interesting talk. We now have time for questions. If you joined us on YouTube, you can put your question in the comment section and I will redirect them to our speaker. If you joined us in Zoom, you can ask you directly. So, questions?
I have a question.
Sure, go ahead.
Yeah. Hi, thank you for the nice presentation. What about data reduction? How will the data be provided?
So you will get 3 types of data. There will be alerts. There will be in yearly data releases, there will be both images and catalogs. So for alerts, you will get them within 60 seconds of closing the shutter. And they will be available to everyone in the world. And they will be distributed with something called Kafka Stream. And that's already operational. For example, our prototype software is used by the Zwicky Transient Factory. So it's a relatively new tool, but people are doing it already. And if you want to get alerts, you would just do the same thing as people do today. Then similar to SDSS, you'll have yearly data releases and you will get reduced images and you will get catalogs. And the access will be via so-called Rubin Science Platform that will be similar as a basic idea to SDSS website or any other survey website, but it will be much more powerful. And in particular, main aspect is that you will not need to download data to your home computer, but you will be uploading your software for analysis. And so you can think of Jupyter notebooks, IPython notebook, that you simply say, give me data according to these rules, and you can access this data, but actually it's not on your computer. You are doing everything on our computer system. And that will be available to everyone with data rights, which includes everyone in US and Chile, plus our international collaborators. And then after 2 years, everything becomes fully public, but then you need to arrange for how to get to data. Our data center is sized not for the entire world, but rather for people that will have data rights. So then you can say, I want a copy of your data set, tell me how much it costs, and then you pay for it, or we still are working out details how exactly that will work. My advice would be find a way to become a data rights holder through agreement with Rubin Observatory, and that will then give you all the tools that you may want to have for your analysis.
Thank you.
Thank you. More questions?
I have. First of all, thank you very much. Željko was great, as always. And I hope that the young people who have benefited, because this project is for them, right? I mean, with a baseline of 10 years, 2033, the student of today will be the researcher of tomorrow. So it's for them that we are looking for. A question, how is the process going about the in-kind contributions? Is it running on time? Is there any news on that front?
The news, the main news is not running on time. It's falling a little bit behind because of basically COVID-induced problems. Everything is running a little bit later. The good news is that we actually, we did receive the report from the committee that was supposed to rank all these proposals. And Bob Blum, the director in operations, is working with agencies. They need to approve all the proposed deals in it. And so we are talking about few months until Bob Blum and Phil Marshall will get back to people who submitted these proposals.
Okay, thank you.
Okay, I have a question also. Željko, I was very impressed by that mirror design, that 3 mirrors design. Was this technology developed for the project, or it's for due to the wide field observations, or
yes,
just
so
adapted?
The original design comes from Roger Angel. He worked on trying to solve the problem of how to have large field of view without optical distortions. That goes back to late 1990s and early 2000s when Tony Tyson and Roger Angel got together and tried to see if this is technically possible. So Roger Angel came up with this Paul Baker design that was a known design in optics. It's called Paul Baker, but it was never applied to a large telescope. And there was one small telescope, I think it was of the order 1 meter size, that used that design, but it was never applied to very large telescope. And then original design had tertiary mirror in a different plane. So there was primary mirror with hole, literally hole in it. And then the tertiary was behind about 1 meter. And then Lynn Sapola from Lawrence Livermore managed to redesign the whole thing so that tertiary mirror was moved back to the plane of the primary, and that allowed us to produce primary tertiary mirror out of one piece of glass, which then minimizes many distortion modes and becomes easier to handle. Does that answer your question?
Yes, yes, thank you very much. Well, we have still time for one last question. While we wait, if there is another question, I will just redirect some comments on YouTube. Edwin David is saying it's an amazing infrastructure. William Abreu thanks you for the amazing presentation and for this incredible opportunity. Okay, so
thank you. Thank you. As Luis said, I hope that many people who are students who listen to this talk today will, a few years from now, use this data and get some excitement out of it. As I always say to my students, you'll be rich and famous.
Well, they may be famous. Rich, I'm not so sure.
Yeah.
Okay, so if there are no more questions, we will now wrap this up. This presentation will be available on our website and on LIneA's YouTube channel. Thank you everyone for attending, and a special thanks to Željko. This was our latest webinar of the year, and we will resume our activities, our webinar activities, in next year's March. Everyone have a great day and also a great holiday break. Hope to see you all back next year. Okay, so bye-bye. Thank you, everyone.
Thank you, Željko. Thank you, everybody.
Happy holidays to everyone.
Thank you.
Thank you, Rodrigo, for your organization skills.
Thank you, Luis.
Ciao.
Ciao, ciao.